Welcome to our inaugural installment of our series on computer network operation.
Hello. In Series 1, we introduce you to network basic, infrastructure, network addressing, network protocols, and cabling. Computer networking is the practice of connecting computers and other devices to share resources and information. It's the backbone of the modern digital world, enabling communication between devices, data transfer, and access to the internet. Here's a primer to get you started. Basic concepts. Nodes. These are the devices connected to the network, such as computers, servers, printers, and routers. Links. Connections between nodes, which can be wired, for example, Ethernet cables, or wireless, for example, Wi-Fi. Data packets. Information sent over the network is broken down into small packets for efficient transmission. Protocols. Rules and standards that govern communication between devices on the network, such as TCP, IP, Ethernet, and Wi-Fi.
Types of networks. LAN, local area network. A network that spans a small geographic area, typically within a single building or campus. WAN, wide area network. A network that covers a larger geographic area, often connecting multiple LANs across cities or countries. Wireless networks. Networks that use radio waves to connect devices without physical cables, such as Wi-Fi and cellular networks. Internet, a global network of networks, connecting billions of devices worldwide. Network devices. Routers, directs traffic between different networks. It connects LANs to form a WAN and connects devices to the internet. Switch, forwards data packets between devices within the same network. It operates at the data link layer, layer 2, of the OSI model. Modem converts digital data from a computer into analog signals for transmission over telephone lines, for DSL, or vice versa. Firewall protects networks by filtering incoming and outgoing traffic based on predefined security rules.
Network topologies. Star, devices are connected to a central hub or switch. Bus, devices are connected in a linear fashion along a single cable. Ring, devices are connected in a circular manner, with each device connected to exactly to other devices. Mesh, devices are interconnected with multiple paths between them, providing redundancy and fault tolerance. Network protocols. TCP, IP, as the fundamental protocol suite of the Internet, consisting of Transmission Control Protocol and Internet Protocol. HTTP and HTTPS protocols as for transferring hypertext, web, documents over the Internet. FTP, File Transfer Protocol for transferring files between computers on a network. SMTP, POP, and IMAP, protocols for sending and receiving email.
Network security. Encryption protects data by encoding it in such a way that only authorized parties can access it. Access control restricts access to network resources based on user credentials or other criteria. Firewalls filters network traffic to prevent unauthorized access and malware infections. Intrusion detection prevention systems, IDS/IPS, monitor network traffic for suspicious activity and take action to prevent security breaches. Understanding computer networking opens up a world of opportunities in IT, telecommunications, cybersecurity, and beyond. It's a foundational skill for anyone working with computers or technology.
That covered the basics of networking. Now, let's progress to network infrastructure.
Computer network infrastructure refers to the foundational components and systems that enable the operation and connectivity of computer networks. It encompasses both physical hardware and software components that facilitate communication and data transfer between devices within a network and beyond. Here's an overview of key elements of network infrastructure. Physical components. Networking devices. This includes routers, switches, hubs, modems, access points, and network adapters. These devices manage and direct the flow of data within a network. Cables and connectors. Ethernet cables, for example, Cat5e, Cat6, and fiber optic cables are used to physically connect devices to the network infrastructure. Wireless infrastructure. Wireless access points, APs, and antennas enable wireless connectivity, allowing devices to connect to the network without physical cables. Network architecture. Topology. The layout or structure of the network, such as star, bus, ring, or mesh topology. LANs and WANs. Local area networks. LANs are confined to a specific geographic area, while wide area networks, WANs, cover larger areas, often spanning multiple locations or even continents. Subnets. Logical subdivisions of a network that help in organizing and managing network resources efficiently.
Networking protocols and standards. TCP/IP. The standard protocol suite used for communication over the Internet and most computer networks. Ethernet. A widely used networking technology for wired LANs, defining how data is transmitted over Ethernet cables. Wi-Fi. Standards like IEEE 802.11 govern wireless networking, enabling devices to connect to wireless LANs. Network services. Domain name system. DNS translates human-readable domain names, for example www.example.com, into IP addresses. Dynamic Host Configuration Protocol, DHCP, automatically assigns IP addresses and other network configuration parameters to devices on the network. Network Time Protocol, NTP, synchronizes the time clocks of computers on a network. Network security measures. Firewalls protect networks from unauthorized access and cyber threats by filtering incoming and outgoing traffic. Intrusion detection systems, IDS, and intrusion prevention systems, IPS, monitor network traffic for suspicious activity and take action to prevent security breaches. Virtual private networks, VPNs, securely extend a private network across a public network, usually the Internet, to enable remote access and secure communication. Management and monitoring tools. Network management systems, NMS, software tools used to monitor, manage, and optimize network performance and security. SNMP, Simple Network Management Protocol, a protocol used for network management and monitoring.
Computer network infrastructure forms the backbone of modern communication and information exchange. It encompasses the physical, logical, and operational components that enable the functioning of computer networks, from basic LANs to complex global WANs.
We've covered infrastructure. All right, let's now shift our focus to network addressing.
Welcome to our exploration of computer network addressing, the crucial system that allows computers to locate and communicate with one another on a network. Computer network addressing involves assigning unique identifiers to devices within a network to facilitate communication and data transfer. These addresses enable devices to send and receive data across the network, ensuring that information reaches its intended destination.
Every device connected to a network is assigned a unique identifier known as an IP address. This address is essential for sending and receiving data accurately. An IP, Internet Protocol Address, is a numerical label assigned to each device connected to a network that uses the Internet Protocol for communication. IPv4, Internet Protocol version 4 addresses are typically represented as 4 sets of numbers separated by periods. Each set can range from 0 to 255. IPv6, Internet Protocol version 6 addresses are longer and represented in hexadecimal format. IPv6 was developed to address the limitations of IPv4 and accommodate the growing number of devices connected to the Internet. There are 2 primary types of IP addresses, IPv4 and IPv6. IPv4 uses a 32-bit address format, while IPv6 uses a 128-bit format to accommodate more devices. Classes and subnetting. IP addresses are divided into classes A, B, C, D, and E, which dictate the range of addresses available for different types of networks. Subnetting involves dividing a network into smaller subnetworks, subnets, to improve efficiency and security. Subnetting allows for more efficient use of IP addresses and helps isolate network traffic. Subnet masks determine the size of the subnet and which part of the IP address represents the network portion and which part represents the host portion.
Network addressing isn't just about assigning numbers. It's structured hierarchically, which helps in routing traffic efficiently across the internet.
IP addresses are divided into classes A, B, C, D, and E, which dictate the range of addresses available for different types of networks. Subnetting is a method used to divide a network into smaller, manageable pieces. This is crucial for enhancing performance and security within large networks. Subnetting allows for more efficient use of IP addresses and helps isolate network traffic. Subnet masks determine the size of the subnet and which part of the IP address represents the network portion and which part represents the host portion.
Dynamic Host Configuration Protocol, or DHCP, automatically assigns network addresses. Dynamic IP addressing assign IP addresses to devices when they connect to the network. Dynamic IP addresses are temporary and may change each time a device reconnects to the network. Static IP addressing involves manually assigning a specific IP address to a device. Static IP addresses do not change over time unless manually reconfigured.
Address resolution comes into play when a device needs to find the hardware address of another device on the same local network. MAC addresses. Media Access Control Address is a unique identifier assigned to the network interface of a device. Unlike IP addresses, MAC addresses are typically hard-coded into the device's hardware and do not change. MAC addresses are used at the data link layer of the OSI, Open Systems Interconnection model, to facilitate communication between devices within the same network segment. DNS, Domain Name System, is a hierarchical system that translates human-readable domain names, for example, google.com, into IP addresses, for example, 192.168.1.1, that computers use to locate and communicate with each other on the internet. DNS eliminates the need for users to remember complex IP addresses and simplifies the process of accessing websites and other internet resources.
Understanding network addressing is fundamental for anyone involved in managing or designing networks, ensuring smooth and efficient communication across digital devices. Computer network addressing is essential for enabling communication and data transfer between devices within a network and across the internet. IP addresses, subnetting, MAC addresses, and DNS are all crucial components of network addressing that help ensure the efficient and reliable operation of computer networks. All right, let's keep the momentum going. Now, allow me to introduce you to protocols.
We live in a world where computers communicate seamlessly, exchanging information effortlessly. This is made possible by computer network protocols. Computer network protocols are a set of rules and conventions that govern communication between devices on a network. These protocols define how data is transmitted, received, and processed across the network, ensuring interoperability and reliable communication. Here's an overview of key aspects of network protocols.
Protocols are the set of rules that dictate how data travels from one device to another over a network. They ensure that devices speak a common language. Types of protocols. Communication protocols. These protocols define how devices communicate with each other. Examples include TCP/IP, Transmission Control Protocol, Internet Protocol; UDP, User Datagram Protocol; and ICMP, Internet Control Message Protocol. Routing protocols, used by routers to determine the optimal path for forwarding data packets within a network. Examples include our IP Routing Information Protocol, OSPF Open Shortest Path First, and BGP Border Gateway Protocol. Application protocols facilitate specific applications or services running on top of the network, such as HTTP Hypertext Transfer Protocol for web browsing, SMTP Simple Mail Transfer Protocol for email, and FTP File Transfer Protocol for file transfer. Security protocols ensure the confidentiality, integrity, and authentication of data transmitted over the network. Examples include SSL, TLS, secure sockets, layer transport layer security for encrypted communication, and IPsec, Internet Protocol security for securing IP packets.
From the moment you send an email to the instant you receive a reply, protocols are at work. They manage the orderly sending and receiving of messages. Transmission Control Protocol Internet Protocol, TCP/IP. TCP/IP is the fundamental protocol suite used for communication on the Internet and most computer networks. TCP provides reliable, connection-oriented communication by establishing a connection between sender and receiver, ensuring data delivery and handling retransmission of lost packets. IP is responsible for addressing and routing packets between devices on the network. It assigns unique IP addresses to devices and determines the best path for data transmission. Consider the Internet Protocol, or IP. It's responsible for routing the packets of data that make up all your online requests and responses. Open Systems Interconnection, OSI model. The OSI model is a conceptual framework that standardizes network communication into 7 layers, each with its own set of protocols and functions. The layers include physical, data link, network, transport, session, presentation, and application. Protocols such as Ethernet, Wi-Fi, TCP, and HTTP operate at different layers of the OSI model.
Then there's the Transmission Control Protocol, or TCP. It takes care of breaking down your data into packets and reassembling them correctly at the destination. Packet switching. Network protocols use packet switching to transmit data across the network. Data is divided into smaller packets, each containing a portion of the original message along with addressing information. These packets are then transmitted independently across the network and reassembled at the destination. Protocols also handle errors and data integrity. If a piece of data gets lost or corrupted, protocols ensure it's sent again and correctly integrated. Protocol standards organizations. Several organizations, such as the Internet Engineering Task Force, IETF, International Organization for Standardization, ISO, and Institute of Electrical and Electronics Engineers, IEEE, develop and maintain standards for network protocols. Standards ensure compatibility, interoperability, and consistency across different network devices and technologies. Computer network protocols are essential for enabling communication and data exchange between devices on a network. They define the rules and conventions for transmitting, routing, and securing data, allowing for efficient and reliable network communication. Security is another crucial aspect managed by protocols. They protect the data sent across networks, ensuring that sensitive information remains confidential. Computer network protocols are the unsung heroes of our digital lives. They keep our digital communications fast, reliable, and secure.
Thus far, we've explored network basics, infrastructure, addressing, and protocols. To wrap up this series, let's delve into network cabling.
In networking, types of cables matters. Welcome to our exploration of data transmission, where we unravel how data zips through networks. Let's start with frequency, the number of times a signal cycles in a second. Frequency. In data transmission, frequency refers to the rate at which a signal oscillates or cycles per second. It's usually measured in hertz. Higher frequencies can carry more data but may face challenges like signal attenuation over long distances. Bandwidth follows closely, defining the capacity of a transmission channel. Essentially, it's the range of frequencies that a channel can effectively handle. Bandwidth refers to the range of frequencies within a signal or channel that can carry data. It's often measured in hertz or bits per second, BPS. A wider bandwidth allows for more data to be transmitted simultaneously.
Now, throughput takes the spotlight. This is the actual rate at which data is successfully transmitted over a network, influenced by bandwidth, among other factors. Throughput is the actual amount of data that can be transmitted over a network or communication channel in a given amount of time. It's influenced by factors like bandwidth, latency, and network congestion. Multiplexing is a clever technique allowing multiple signals to share the same transmission medium. It efficiently uses the available bandwidth and enhances data flow. Multiplexing is the technique of combining multiple data streams into a single signal for transmission over a shared medium. There are different types of multiplexing, including time division multiplexing, TDM, frequency division multiplexing, FDM, and wavelength division multiplexing, WDM. Multiplexing increases the efficiency of data transmission by allowing multiple users or signals to share the same communication channel.
However, data transmission isn't flawless. Common issues include noise, interference, and attenuation, all of which can degrade the quality of the transmitted data. Some common transmission flaws include noise, interference or random signals that disrupt the original transmission, reducing the signal quality. The weakening or loss of signal strength as it travels over a medium, often due to factors like distance or interference. Delay, the time it takes for data to travel from the sender to the receiver, influenced by factors like network congestion and propagation delay. Jitter, variability in the timing of data packets or signal arrival, which can affect the reliability of communication. Crosstalk, unintentional coupling of signals between communication channels, leading to interference and signal degradation. Interference and noise disrupt the signal clarity, while attenuation refers to the loss of signal strength over distance or due to obstructions. By understanding these fundamental concepts, individuals can make informed decisions when designing, implementing, and troubleshooting digital networks. Whether you're a network engineer, IT professional, or everyday user, a grasp of these principles is essential for optimizing network performance and ensuring seamless communication experiences.
Concluding Series 1. So, these are the subjects you'll want to delve into if you're pursuing a career in computer networking. Stay tuned for Series 2.